All right, so section 1.4, inverse functions. So learning objectives, we have 1.4.1, determine the conditions for when a function has an inverse. And we're going to see that this is when a function is 1-to-1, right? And written out there. Now, 1.4.2, use the horizontal line test to recognize when a function is 1-to-1. So this is already giving us conditions under which a function is 1-to-1, and that we're going to see that when we use the horizontal line test. Find the inverse of a given function. We'll see how to do that. Draw the graph of an inverse function. Yep, we'll go over that. And then evaluate inverse trigonometric functions. So we'll go ahead and go over that as well. So let's go ahead and just read this section. An inverse function reverses the operation done by a particular function. So this is the main idea here that we need to kind of, overall, this is what we see. An inverse function reverses the operation done by a particular function. In other words, whatever a function does, the inverse function undoes it. In this section, we define an inverse function formally and state the necessary conditions for an inverse function to exist. We examine how to find an inverse function and study the relationship between the graph of a function and the graph of its inverse. Then we apply the ideas to define and discuss properties of the inverse trigonometric functions. So that's basically just restating the learning objectives. So let's start with the existence of an inverse function. We begin with an example. Given a function f and an output y equals f of x, we are often interested in finding what value or x values are mapped to y by f. For example, consider the function f of x equals x cubed plus 4. Since any output y equals x cubed plus 4, we can solve this equation for x to find that the input is x equals the cube root of y minus 4. So basically, we just took the function y equals x cubed plus 4. We subtract 4 on both sides, and then take the cube root of both sides. And so we have that the x value is equal to the cube root of y minus 4. Okay, now notice that this defines x as a function of y. Denoting this function, f inverse, and writing x equals f inverse of y equals the cube root of y minus 4, we see that for any x in the domain of f, f inverse of f of x, which is f inverse applied to x cubed plus 4 is equal to x. Okay, so basically what that's saying is that this function here, if you think of it as a function of y, undoes what this function up here does, right? So let's go ahead and write it out. X is equal to f inverse of y, which is equal to the cube root of y minus 4. And so here we're going to take what y is from our original definition and we'll plug it in to this inverse function. So f inverse of y is going to be equal to the cube root of y minus 4, but y is x cubed plus 4, and then we have that minus 4. And then so we see that if we simplify the inside, there's a plus 4 and a minus 4. Those plus 4 and minus 4 would cancel. So we get the cube root of x cubed, and this gives us just x. So we see that when f inverse was applied to, we really could write this y as f of x, y equals x cubed plus 4. We can write as f of x equals x cubed plus 4. So when f inverse was applied to f of x, the result was just x, right? So here we applied f to some value x, and then we applied f inverse to that function value, and we get x. So essentially, we can say that F inverse undid what F did because the original input ended up being the output. Okay, so thus this new function, F inverse, undid what the original function F did. A function, excuse me, a function with this property is called the inverse function of the original function. Okay, so let's go ahead and go over the definition. Given a function F, so we have a function, and I'll write it, I'm just writing in the margins here. We're just reading the textbook. So given a function F with domain D and range R, so here is a function, it is defined on a certain domain, and then the values of that domain are mapped to another set, which we call the range R. Its inverse function, and here's a big if it exists, is the function F inverse with domain R and range D. So notice that the domain and range are flipped around here for the inverse function. And then we're given this such that F inverse of Y equals X if F of X equals Y. In other words, for a function F and its inverse F inverse of F of X is equal to X for all X in the domain of D, and F of F inverse of Y equals Y for all Y in the range R. Okay, so let's go ahead and take a look at, just break this down a little bit, and then we'll get to the examples, which is, we'll get a lot from those examples. So first of all, let's go over just this part here that I'm highlighting. F inverse of Y equals X if F of X equals Y. So if you have two inverse functions, and we'll use the one that they gave as an example. So the two inverse functions that we're talking about here are F of X equals X cubed plus 4. And then the inverse function is F inverse of X is equal to the cube root of X minus 4. So let's take a value X. Let's say if X is equal to 1, let's just take a simple number. We plug it into the function F. F of 1 is equal to 1 cubed plus 4. And so we see that F of 1 is equal to 1 cubed is 1 plus 4 is 5. So F takes the value 1 and maps it to 5, right? So what is F inverse going to do to the value 5? It's going to undo. Notice that F sent, it took in 1 and it transformed it basically under its rule to 5. Now F inverse is going to take 5, and when we plug in 5, we have 5 minus 4. 5 minus 4 is equal to 1. And so F inverse of 5 is 1. Notice that F inverse took the value 5 and then it mapped it right back to 1. So we see that these two are inverse functions. They undo each other. Now, all right, so yeah, let's go ahead and continue. Note that F inverse here is read as F inverse. Here, the -1 is not used as an exponent, and it's important to know that F inverse of X is not equal to, so F inverse of X, this is just a notation to show that this is the inverse function of F. It does not mean the reciprocal of the function F of X, okay? This is incorrect. This little -1 is just a notation to say that that function there, F inverse, is the inverse function of F. Figure 1.37, shows the relationship between the domain and range of f and the domain and range of f inverse. And we'll see this in some later examples, I believe. But this example that we've done here is not going to show this as well. But yeah, so we can see that 1 was mapped to 5 by f. So notice if the number 1 was here in the domain of f, f mapped it over to the range, the value of 5. But then what does the function f inverse do to that value 5? It maps it right back over to 1, right? So they undo each other. So figure 1.3.7 or 1.37, given a function f and its inverse f inverse, if we apply f inverse to some y value and you get x, then because f inverse is the inverse of f, this is equivalent to saying, so this occurs if and only if f maps x to y. That is essentially how we're defining the inverse function. So because of this, the way that they undo each other, the range of f becomes the domain of f inverse, and the domain of f becomes the range of f inverse. We'll see this more in an example later. Recall that a function has exactly one output for each input. Yeah, so we should have one output for each input. So when we plugged in 1 for f, when we plugged 1 into f, we should get exactly one output there. So therefore, to define an inverse function, we need to map each input to exactly one output. Okay, because the inverse function, we're kind of defining it in the name for it. We will also want it to be a function. So we need to map each of its inputs exactly to one output. For example, let's try to find the inverse function for f of x equals x squared. Solving the equation y equals x squared. So we take f of x equals x squared. We change it to y equals x squared. And we're going to try to solve this for x. Well, what we would do is we would take the square root of both sides. And I'm going to flip things around here. So we have the square root of x squared is equal to the square root of y. It turns out that the square root of x squared is equal to the absolute value of x and this is equal to the square root of y. So x is equal to plus or minus the square root of y. And so it says we arrive at this equation. And now it says this equation does not describe x as a function of y because there are two solutions to this equation for every y larger than 0. So let's go ahead and take a look at this. If y is equal to 4, then is this equation here describing x as a function of y? And the answer turns out to be no, because if y equals 4, then x is equal to plus or minus the square root of 4. And this is two different numbers. This is plus the square root of 4, and this is minus the square root of 4. And so we get positive 2 and negative 2. We see that an input of y equals 4 gives us two outputs of x equals 2 and x equals negative 2. And so that fails to be a function. So let's read on. The problem with trying to find an inverse function for f of x equals x squared is that two inputs are sent to the same output for each output y larger than 0. So if we take a look at the function y equals x squared, this is a function because it passes the vertical line test. But as you can see, for an x value of +2 and an x value of -2, and this is just a little sketch here, we have the same y value of 4, right? This is the function f of x equals x squared. For 2 and -2, the same y value 4 occurs. And so that's what this is saying. The problem with trying to find an inverse function for f of x equals x squared is that 2 inputs, and these inputs are the ones I've written here, these 2 inputs are sent to the same output for each output y greater than 0. So for like the value 4, there are 2 inputs that are going to be sent to that output. So when you invert the function, then there is one output like 4 that is going to be, or one input, excuse me, that is going to be set to 2 outputs, as we've seen in this example here. Okay, so we can't have multiple inputs being sent to the same output, because if we try to invert the function, then we're going to run into a problem where one input will be sent to multiple outputs. The function f of x equals x cubed plus 4 discussed earlier did not have this problem. For that function, each input was sent to a different output. And you may know what x cubed plus 4 looks like. I'm just going to give a quick sketch here. It would be 1, 2, 3, 4, something like this. Okay. And what is the difference? We're going to see coming up here pretty soon. But the x cubed plus 4 does have an inverse function because it passes the horizontal line test. Notice that here, this function will not pass the horizontal line test. A function that sends each input to a different output is called a one-to-one function. So here we have a one-to-one function. And then f of x equals x squared is not one-to-one because it does not send each input to a different output. Namely, the inputs 2 and -2 are actually sent to the same output of +4, and it fails to be one-to-one for that reason. Here's the formal definition for one-to-one. A function, we say a function f is a one-to-one function if the output value of x1 is not equal to the output value of x2, f of x2, when x1 and x2 are not equal. So let's go ahead and show how f of x equals x squared fails to be one-to-one. Notice if x1 is equal to -2 and x2 is equal to +2, then f of x1 is equal to 4 and f of x2 is equal to 4. So notice that x1 is not equal to x2. That's what we're talking about here. And so f of x1 should not be equal to f of x2 if this function is one-to-one, but we see that they're both equal to 4. So then this function is not one-to-one, right? And again, you can see that it fails the horizontal line test. So one way to determine whether a function, oh, and there are those functions right there. One way to determine whether a function is one-to-one is by looking at its graph. If a function is one-to-one, then no 2 inputs can be sent to the same output. Therefore, if we draw a horizontal line anywhere in the xy plane, according to the horizontal line test, it cannot intersect the graph more than once. We note that the horizontal line test is different from the vertical line test. Yeah, because the vertical line test determines whether a graph is the graph of a function or not. And the horizontal line test determines whether a function is one-to-one. Right? So vertical line test is to determine, first of all, is it even a function? And then once you know it's a function, the horizontal line test is used to determine whether or not it's one-to-one. So here's our rule. The horizontal line test, a function f is one-to-one if and only if every horizontal line intersects the graph of f no more than once. Okay, so not one-to-one, one-to-one. Figure 1.38, the function f of x equals x squared is not one-to-one because it fails the horizontal line test. And then part B, x cubed is one-to-one because it passes the horizontal line test. No matter where you draw a horizontal line, any single horizontal line that you draw will intersect the graph in, at most, one place. Okay, so here's a couple of examples, and these are kind of nice. You can pause the video if you want. Example 1.28, determining whether a function is one-to-one. For each of the following functions, use the horizontal line test to determine whether it is one-to-one. Okay, well, we can do this. Let's see here. Yeah, we got two functions here. So for part A, yeah, basically, let's use the horizontal line test. There we go. There's a horizontal line right there. And we can see that if you put this horizontal line in the right spot, it does intersect more than once. So this is not one-to-one. Now, what about the function y equals 1 over x, or f of x equals 1 over x? It doesn't really matter where you draw your vertical line. It's going to intersect in, at most, one place. Right, so even when you get really close here, you might think maybe it's going to intersect in more than one spot. No, but this function is decreasing and getting closer to zero. So no horizontal line will intersect more than once. So it does pass the horizontal line test. Oops. And so this is one-to-one. We can write it out. One-to-one. So solution, since the horizontal line y equals n for any integer n greater than or equal to 0 intersects the graph more than once, this function is not one-to-one. Yeah, and so we looked at n equals 2 or y equals 2. And that intersects the graph more than once, so it's not one-to-one. And then for part B, oh, there's an example there. For part B, it says since every horizontal line intersects the graph once, at most, this function is one-to-one. There. Now you can think about this one yourself. Is the function f graphed in the following image one-to-one? If you pause the video, I will answer the question. The horizontal line test tells us that this is not one-to-one. Because back to the horizontal line test, f is one-to-one if and only if every horizontal line intersects the graph of f no more than once. Kind of worded a little funny there, but I mean, not funny, but that's how it needs to be worded. There is a line here that does intersect more than once, so it is not one-to-one. Okay, so how do we find a function's inverse? Finding a function's inverse. We can now consider one-to-one functions and show how to find their inverses. Recall that a function maps elements in the domain of f to elements in the range of f. The inverse function maps each element from the range of f back to the corresponding element from the domain of f. Therefore, to find the inverse function of a one-to-one function, given any y in the range of f, we need to determine which x in the domain of f satisfies f of x equals y. Okay, we'll get to an example here pretty soon. We're just reading through. Doing so, we are able to write x as a function of y, where the domain of this function is the range of f, and the range of this new function is the domain of f. Consequently, this function is the inverse of f, and we write x equals f inverse of y. Since we typically use the variable x to denote the independent variable and y to denote the dependent variable, we often interchange the roles of x and y and write y equals f inverse of x. Representing the inverse function in this way is also helpful later when we graph a function f and its inverse f inverse on the same axes. Okay, so here's our problem solving strategy. Solve the equation y equals f of x for x, then interchange the variables x and y and write y equal to f inverse. So let's go ahead and take a look at an example here. And we'll do the example, even though it's already done, we'll just do it again. Okay, so let's take a look here. Okay, so we have a function f of x equals 3x minus 4. And it says to solve this equation, y equals f of x for x. Now, the first step that they generally show in pre-calculus class is to, change f of x to y. Then it does say to solve for x. Okay, let's go ahead and solve for x. Plus 4, plus 4. And what does this give us? Y plus 4 equals 3x. And then we can divide by 3 on both sides. And so we get x on the right-hand side. On the left-hand side, we get, I'll line up with what the book is writing here, 1/3 y, or y divided by 3, plus 4 divided by 3. So we have x equals 1/3 y plus 4/3. And now we can interchange the variables x and y. So y equals 1/3 x plus 4/3. And then write y as f inverse. So we'll use the notation, instead of y, we'll write it as f inverse of x equals 1/3 x plus 4/3. And this is the inverse function. There we go. It does ask us to state the domain and range of the inverse. And so there's actually a couple ways that we could do this. First of all, let's go to f. For f, what is the domain of f? Now, if you take a close look at f is a linear function, y equals 3x minus 4. It has, I'm just going to give a rough sketch here, 1, 2, 3, 4. It has a, something like this. You can get a more accurate graph online. But the domain is all real numbers, -infinity to +infinity. The range of this function turns out also to be all real numbers, -infinity to +infinity. So we can find the domain of f inverse. And I'll write in a different color. The domain of f inverse is actually going to be the same as the range of f. So that is -infinity to +infinity. And then the range of f inverse is going to be the same as the domain of f. So in this case, it's not too exciting here because the domain and range are the same thing, but maybe we'll see an example later if they have one in the book of, one that's a little different. But the range of f inverse is -infinity to +infinity. Now, of course, we could have just seen that as well because this is another linear function. It has a positive slope. The domain of these linear functions is generally all real numbers, -infinity to +infinity. And then the range, since it has a positive slope, would end up also being -infinity to +infinity. We could just determine that just by thinking about the function. Okay, so they run through the steps here. Step 1, step 2, we did those. Yeah, we did that. Since the domain of f is all real numbers, the range of f inverse. So notice they did the same thing there. The range of the original function f gives you the domain of the inverse function. And then how do we verify that applying one function to the other gives us just x in return? Well, let's go ahead and take a look at how we would do that. We want to apply f inverse to the function f of x. Okay, so first of all, what is f of x? F of x was given to be 3x minus 4, so I'll make a replacement there. And then f inverse was 1/3 times its input plus 4/3. But then the input here that we're plugging into f inverse is f. So we're going to plug in 3x minus 4. And so this is what we have. Let's go ahead and see if this simplifies. When you apply the inverse function to the original function, do they cancel each other out? Essentially is what we're asking here. We distribute the 1/3. And so we get 1/3 times 3x is just x, minus 1/3 times 4 is 4/3, plus 4/3. This gives us, these cancel, and we get x. So notice that f inverse applied to f was just x. So then these, we're further verifying here that these are inverse functions. All right. So graphing inverse functions. Let's consider the relationship between the graph of a function f and the graph of its inverse. Consider the graph of f shown in figure 1.39. Okay, and a point AB, so notice there's a point here, just some arbitrary point AB on the graph. So what does it mean, to have a function y equals f of x and then a point AB on the graph? If y is equal to f of x, then notice that for the point AB, well, these are x and y values, right? And so we can consider these as x and f of x because they're an ordered pair. So the y value is the output from the function f when you plug in the input x. So then we can say that this is a and f of a. So f of a is equal to b. And that's what they're saying here. So b, the y value, is just f of the input a. But then remember that this is equivalent to if b equals f of a, or if f of a is b, meaning that a gets mapped to b under f, then what does f inverse do to b? It sends it back to a. And that's what we're saying in this box here. So what does this tell us now? What does f inverse of b equal to a tell us? Well, that tells us that if you plug in b into the inverse function, you get an output of a. And that tells us that the point BA is on the graph of f inverse. So it says, well, let's continue here. Therefore, when we graph f inverse, the point BA is on the graph. As a result, the graph of f inverse, it turns out f inverse is a reflection of the graph of f about the line y equals x. So there was the point AB right here. So we know that we can switch those coordinates. And when we switch them, we get BA, and that is a point on the inverse function. And it turns out that we can do this for any point. So for this point here, I'll draw it nice and big. Right, you choose a random point on the graph of f, you switch the coordinates, that is going to be a point on F inverse. And if you do it for, every single point on F, then you will get all of the points of F inverse. And so this results in these two functions being reflections of each other about the line y equals x. All right, so figure 1.39, the graph of this function f shows point AB on the graph of f. Since AB is on the graph of f, the point BA is on the graph of f inverse. Then the graph of f inverse is a reflection of the graph of f about the line y equals x. So it's a pretty cool result there. When I took this class myself, my teacher had me draw a single function like this one here, and then draw the line y equals x like that, and told us, use your pencil to shade this in really good with your pencil. And then you fold your piece of paper along this line y equals x, and you press down really hard, and then you would end up getting, your pencil would smear onto the other side, and then tried to ask us, figure out what this function is. And we figured out what the function is, and we saw, oh wait, that's actually the inverse of f. So it's kind of a cool result there. Okay, so sketching the graphs of inverse functions, this should be fairly easy now. You just take a point like -2, 0, and if you flip it, you get 0, -2, and that is a point on the function f inverse. Let's take another one here. Let's just make this up. 0 is the x coordinate. The y coordinate, let's say, is 1.3. I'm not sure if that's exactly what it is, but so then 1.3, 0 is a point on the function f. And so we can kind of sketch that there. And this is f inverse of x. Okay. Now, of course, and this is actually what I was just talking about. If you drew the line here, y equals x, and you fold the piece of paper, then this should be a reflection. And my sketch is roughly a reflection there. Now, what does this look like? This looks like half of a parabola, right? So just to kind of give a little bit more insight, they actually do it right there. Let's take this function, f of x, and you know what? We'll do it in blue here. F of x equals the square root of x plus 2. Y equals the square root of x plus 2. And then they said solve for x in the step. So we'll square both sides. So y squared is equal to x plus 2. And then we subtract 2 on both sides. So y squared minus 2 equals x. And then I'm going to just flip this around so we have the x on the left-hand side, y squared minus 2. And what else was I going to do? Yeah, then they said interchange y and x. So y equals x squared minus 2. And notice that this is the function, this is the equation of a parabola, right? So we can say this is f inverse now. And this is x squared minus 2. But what we got for our answer is not a full parabola, right? It's just half of a parabola. Now, why is that? We can take a look at, answer these questions yourself here. What is the domain of this function? The domain of f is equal to, if we look at the graph, the domain is, this here, from -2 to infinity. The range of f is equal to 0 to infinity. Right, along the y-axis, we can go as low as 0, and then go up to infinity. So then what is the domain and range? So even though this looks like it's going to be a parabola here, what is the domain of f inverse of x, or f inverse? Well, this is going to be the range of f, which is from 0 to infinity. And notice that's exactly the domain of the function f. It can go as far left, I'll shade the point nice and big here, as far to the left as 0, x equals 0, and then it only moves to the right. So that's domain of 0 to infinity. And then what is the range of f inverse? The range of f inverse is going to be the domain of f, which is -2 to infinity. And that's exactly what we see there. This function goes as low as a y value of -2, but it doesn't go any lower than that. Now, so just to point this out here, why isn't it the full parabola? Right? If it was the full parabola, when you inverted this function, well, first of all, this would not be 1-to-1, so it would not have an inverse function. But even, say you could invert it, if you reflected this about the line y equals x, this full parabola here, then the reflection would be this, which is not a function because it does not pass the vertical line test, right? So restrictions need to be made on these domains here in order for these functions to have inverses. Okay, there's a lot of stuff to say here, but we're just kind of reading through the textbook, trying to get a refresher here on this is a review, right? Okay, so let's just read it quickly here. Reflect the graph about the line y equals x. The domain of f inverse is 0 to infinity. That's what we said. The range is -2 to infinity. By using the preceding strategy for finding inverse functions, we can verify that the inverse function of f, the inverse function is f inverse, which is x squared minus 2. As shown in the graph. There we go. Yep. Now, all right, very good. Cool stuff there. So restricting domains, as we have seen, f of x equals x squared does not have an inverse function. So if we take a look at this, this does not have an inverse function because it's not 1-to-1, right? It fails the vertical or the horizontal line test. However, we can choose a subset of the domain of f such that the function is 1-to-1. This subset is called a restricted domain. So you can see that this function here fails the horizontal line test. Crosses in more than one spot. So the domain of f, let's go ahead and write f of x equals x squared. The domain of f is equal to all real numbers, -infinity to +infinity. So what if we restricted this domain? Let's go ahead and keep reading. By restricting domain of f, we can define a new function g such that the domain of g is the restricted domain of f, and g of x equals f of x for all x in the domain of g. So we're going to define a new function. Let's call it g of x. And let's see, I'll write it. I'm going to draw it right on top. Here's a new function. I'm going to draw it in red so it's clear. Oh, there's a new function. This new function, let's call it g, and g of x is actually equal to x squared. It's defined in the same way, but the domain of g is only from 0, and let's include 0, from 0 to infinity. Notice that this is now, this is a function, and this is now 1-to-1, because if you draw a horizontal line, do we ever cross the red function more than once with any horizontal line? The answer is no, because we've basically removed half of the function f and defined that to be a new function. So notice one more time here, we defined a new function g such that the domain of g is the restricted domain of f. So notice the domain of g is just part, it's basically half of the domain of f, but it turns out that g of x is the same as f of x for all x in the domain of g. Yeah, and you can see they are identical. They're defined identically, and then you can see that the function, the actual graph, is identical on the restricted domain of g. Then we can define an inverse function of g on that domain. So now, even though f of x equals x squared did not have an inverse function because it's not 1-to-1, G can have an inverse function. For example, since f of x equals x squared is 1-to-1 on the interval from 0 to infinity, and I believe this should say is not 1-to-1 on the interval 0 to infinity. Oh, sorry. Yeah, so for example, since f of x equals x squared is 1-to-1 on a restricted interval from 0 to infinity, we define the function g on that domain. We define its domain to be 0 to infinity. And so g of x is equal to x squared in that domain from 0 to infinity. And then g is a 1-to-1 function. So it has an inverse function. And what is the inverse function going to be? Well, I think we solved it earlier, but just in case we didn't. So g of x is equal to x squared. So we say y equals x squared. And then we take, let me write this as x squared equals y. We take the square root of both sides. Now, the square root of x squared is the absolute value of x, which is equal to the square root of y. But here, remember that x is in the domain of g, which is from 0 to infinity. So x is larger than or equal to 0. So therefore, the absolute value of x here is no longer equal to plus or minus the square root of y. X is just going to be equal to the positive square root of y. And then interchanging y and x, we get y is equal to the square root of x, or, and not f inverse, but g inverse of x is equal to the square root of x. Let's continue reading. On the other hand, the function f of x equals x squared is also 1-to-1 on the domain from negative infinity to negative infinity to 0. So we could have also defined, the function to be on this side only, rather than only the right side. So therefore, we could also define a new function h, such that the domain of h is negative infinity to 0, but h of x is still equal to x squared for those values x from negative infinity to 0, the domain of h. So h would also be a 1-to-1 function, and so it would also have an inverse. So h of x is equal to x squared, y equals x squared. If we take the square root of both sides, then we have the square root of y equals x. Now keep in mind here that x is less than or equal to 0 in this case, because the domain we define to be negative infinity to 0. And so if x is less than or equal to 0, and I should have a square root of, the square root of x squared is equal to the square root of y. The square root of x squared is still the absolute value of x. But the absolute value of x, when x is less than or equal to 0, this would be equal to negative x, which is equal to the square root of y. And so if you solve for x, we can do that by dividing by -1 on both sides. We get negative square root of y. And so we get, interchanging x and y, we have y equals negative the square root of x. And so I always resort to f because it's the one I'm more comfortable with, but this is h inverse of x is equal to the opposite of the square root of x. So there's an inverse function there. So as long as we choose our function in a way where it's 1-to-1, we can find an inverse function for it. And notice if we restricted the, let's draw these inverse functions. In green, I will draw g inverse of x. G inverse of x would be the inverse of x squared on this restricted domain where x is larger than or equal to 0, and we would get this roughly, the square root of x. I hope you are familiar with the function the square root of x. Notice its range is from 0 to infinity. But then we could also draw the inverse of h. And that's just going to be the other part of the square root of x. Notice that together, they do not form a function. That's why they are separate inverse functions. All right, so lots of good stuff there. All right. Yeah, so then it just shows G and its inverse on the same set of axes, and H and its inverse on the same set of axes as well. So restricting domains here. Excuse me. Consider the function f of x equals x plus 1 squared. Sketch the graph of f and use the horizontal line test to show that f is not 1-to-1. Okay, and this is a pre-calculus topic. So this is just a parabola shifted to the left 1 unit, and that's exactly what we see. This is at -1. So you can draw a lot of horizontal lines that would intersect more than once. So we can see that f is not 1-to-1. Now for part B, it says show that f is 1-to-1 on the restricted domain from -1 to positive infinity. I'll highlight that in red. From -1 to positive infinity. We can see that it is 1-to-1. Determine the domain and range for the inverse of f on this restricted domain and find the formula for f inverse. Okay, so let's see here. The domain of f. So the domain and range for the inverse, for the inverse of f on the restricted domain. So the domain of f, let's look at that. That is, for this restriction here, it is from -1 to infinity. The range of f, we can see that is from 0 to infinity. So then the domain of f inverse, that is going to be 0 to infinity. The range of f inverse is going to be -1 to infinity. And then it asks us to find a formula for it. Find a formula for f inverse of, or f inverse. Okay, so remember we have f of x equals x plus 1 squared. And this is for x being larger than or equal to 1. So we let y replace f of x. Take the square root of both sides. Now, let me rearrange here. So the square root of x plus 1 squared is equal to the square root of y. The square root of x squared, or the square root of a square, that this is going to give us the absolute value of x plus 1 is equal to the square root of y. Since x is greater than, and I should have put a -1 here, since x is greater than -1, greater than or equal to -1, then the absolute value of x plus 1 is always going to be equal to just x plus 1. And this is equal to the square root of y. Then we subtract 1 on both sides, and we have x is equal to the square root of y minus 1. Switching x and y, we have y equals the square root of x minus 1. And so f inverse of x is equal to the square root of x minus 1. And if you're familiar with your pre-calculus, this is fairly easy to graph. This is just going to be the square root of x function shifted down 1 unit. And so that's going to be roughly something like this. Now let's check the domain by looking at the graph. The domain of f inverse, it looks like, is from 0 to infinity, which matches what we said earlier. Right? The range of f inverse is, since it got shifted down 1 unit, is -1 to infinity. which matches exactly what we said earlier. So everything seems to be matching up, and that's good. All right, so the domain and range of f inverse are given by the range and domain of f, yes. Therefore, the domain of f inverse is 0 to infinity. The range is from -1 to infinity. To find the formula for f inverse, we solve the equation y equals x plus 1 squared for x. If y equals x plus 1 squared, then x is equal to -1 plus or minus the square root of y. So notice here they actually put plus or minus the square root of y, but they say since we are restricting the domain to the interval where x is larger than or equal to -1, we need the plus or minus the square root of y to be larger than or equal to 0. So we only choose the positive part of that. And we did that earlier when we said we had the absolute value of x plus 1, and it ended up just being the positive square root of y. We did not have to put a negative there. Yeah, and so they got the same result. All right, very good. So now the inverse trigonometric functions. Yeah, we'll talk a little bit about these, and then we'll see a couple examples before we finish. We're almost done. All right. The 6 basic trigonometric functions are periodic, and therefore they are not one-to-one, right? So you know, like sine of x is not one-to-one. However, if we restrict the domain of the trigonometric functions to an interval where it is one-to-one, then we can define its inverse. Consider the sine function, and it says figure 1.34. That's okay, I'm not sure where that is. Okay. The sine function is one-to-one on an infinite number of intervals. And let's just quickly sketch it here. Yeah, so we can restrict it in many different ways to be one-to-one. So here's, one period of the sine function. I'll draw another period there, and maybe one going backwards. Oops, yeah, something like that. There we go. So it's periodic, right? It's definitely not. Nope. If you draw a horizontal line, okay, it's not working. It's not one-to-one, right? We can see that. So, but the standard convention is to restrict the domain to the interval -pi/2 to pi/2. Yeah, if you take a look at this function on the interval from -pi/2 to +pi/2, we get this piece of the sine function. And notice that on that blue piece, the function is one-to-one, and the range is from -1 to +1. So it says by doing so, we define the inverse sine function on the domain -1 to 1, such that for any x in the interval from -1 to +1, the inverse sine function tells us which angle theta in the interval from -pi/2 to pi/2 satisfies the sine of theta equal to x. Similarly, we can restrict the domains of the other trigonometric functions to define inverse trigonometric functions. Which are functions that tell us which angle in a certain interval has the specified trigonometric value. Okay, so yeah, let's just break that down a little bit. What it basically said was the function f of x equals the sine of x. Notice that the domain of this function f is equal to all real numbers, right? There are many periods. The range of f is equal to -1 to 1. This is without any restrictions. This is the function f of x equals sine of x. So we're going to define a new function. Now, we could just call it f again, but I'll call it g for right now. And I'll draw it in blue here. G of x is equal to the sine of x. We're defining a new function, which I've graphed there in blue. And the domain is going to be restricted. The domain of G is actually going to be from negative pi over 2 to pi over 2. This function in blue is 1-to-1, as you can see from the graph in blue. The range of G, notice we choose it in this way from negative pi over 2 to positive pi over 2. This is how it's conventionally done. But the range, notice that it's going to be still retain its range, even though we restricted its domain. It retains the range from negative 1 to 1. And so now that we have a 1-to-1 function, this new function g of x, we can define g inverse. And g inverse of x, we give it the notation sine inverse of x, or sometimes g inverse of x. Sometimes people call it arc sine of x. Well, what is the domain of g inverse going to be? Well, we know from our study of inverse functions that this is just going to be the range of g. The domain is going to be from negative 1 to 1, and the range of this function g inverse is going to be from negative pi over 2 to positive pi over 2. All right, and we'll see more about how this works coming up. The inverse sine function denoted sine inverse or arc sine, and the inverse cosine function denoted cosine inverse or arc cosine are defined on the domain D, which is going to be all x values between negative 1 and positive 1, including negative 1 and positive 1. That's what we just talked about. And this is true about inverse functions. Sine inverse of x is going to be equal to y if and only if sine of y is equal to x. And y, the range of g inverse, the range of sine inverse, we said is from negative pi over 2 to positive pi over 2. Okay, I'm not going to read all of these because, they're all defined in a similar way. But we'll see examples to kind of see how this works. Okay, and here are the graphs. So to graph the inverse trigonometric functions, we use the graphs of the trigonometric functions restricted to the domains defined earlier, and then reflect the graphs about the line y equals x. Okay, that's nice. All right, so how do we actually evaluate these? So now we're going to get into some intricate stuff here, and then we're going to be done. So let's go ahead and do this. Oh my gosh, this is a long video. But yeah, sometimes it takes a little while to read through these things. Okay, so when evaluating an inverse trigonometric function, the output is an angle. So this is very important here. When evaluating an inverse trigonometric function, the output is an angle. For example, to evaluate cosine inverse of 1/2, we need to find an angle such that the cosine of theta is equal to 1/2. So let's go ahead and take a look at how we could answer this. If we used, I'm just going to sketch cosine here, so it's not going to be super accurate, but here's a sketch of cosine. Right, so here is 1. We know that cosine goes up to 1. Here's 1/2. So where is cosine of theta equal to 1/2? And we see it's actually equal in a lot of different places right here, right? Well, at least 2. And then if we kept on drawing more periods, there would be even more places where cosine of theta is equal to 1/2. But we need to remember the restricted domain of cosine. And we didn't talk about it too much, but we said it in class. The range of cosine inverse is from 0 to pi. So the domain of the restricted cosine is from 0 to pi. And so pi is right here. And so notice that that is going to avoid having multiple answers because we are only considering this portion here. Okay. And now this is pi over 2, of course. And so here it says that clearly many angles have this property. However, given the definitions of cosine inverse, we need the angle theta that not only solves this equation, but also lies in the interval from 0 to pi. And that's exactly what we were just talking about. So we conclude that the cosine inverse of 1/2 is pi over 3. Now, how did we get that? We've talked about this in class. Here's 0. Here's, pi over 2. Here's pi, right? If we're looking at, these two quadrants here, quadrant 1 and quadrant 2, then the cosine of which angle gives us 1/2? Well, from quadrants 1 and 2, quadrant 1 would give us a positive cosine. So we're looking in quadrant 1. There's some angle here in quadrant 1 whose cosine is 1/2. Well, the cosine being 1/2, if we remember our definition of cosine, this is going to be the adjacent side divided by the hypotenuse. The ratio there has to be 1/2. And so we've seen this triangle before. If we use the Pythagorean theorem, that would tell us that this is equal to the square root of 3, which is positive, of course, because we're in quadrant 1. And you remember this as one of our special right triangles. This was equal to the angle. This is the 30, 60, 90 triangle. Of course, this is 90 degrees. And this angle here, theta, is pi over 3, or 60 degrees. And that is how they got this answer here. The cosine inverse of 1/2 is the angle whose cosine is 1/2. The angle must be between 0 and pi, and its cosine must be 1/2. The only angle that does that, or that has that property, is pi over 3. All right. Next, we now consider a composition of trigonometric functions, of a trigonometric function and its inverse. For example, consider the two expressions sine of sine inverse of the square root of 2 over 2 and the sine inverse of the sine of pi. Now, let's go ahead and see. We might need an extra page here to explain this. So it does say here, the first one we simplify as follows. And I guess you can do this here on your own. The sine inverse of the square root of 2 over 2, this entire thing here is just equal to pi over 4. Now, how do we get this? Since, this is, we're starting this material here, let's go ahead and take a look at that. The sine inverse of the square root of 2 over 2, this is an angle in the interval from negative pi over 2 to pi over 2. So let me call it an angle theta in that interval, with the sine of theta being equal to the square root of 2 over 2. Okay, so we're looking for an angle in this interval. Let me go ahead and write the interval, a negative pi over 2 to positive pi over 2. So we're restricting ourselves to quadrant 1 and to quadrant 4. But we want the sine of this angle to be a positive number. And so that means that this angle is going to have to be in quadrant 1. Because if it were in quadrant 4, the sine of it would be negative. Okay, so now we're in quadrant 1. And the sine being equal to the square root of 2 over 2 means that the opposite side is, or the ratio of the opposite side to the hypotenuse should be square root of 2 to 2. And that's what I've constructed there. If we use the Pythagorean theorem, we will see that the remaining side has to be of length square root of 2. And then it turns out that this is a special right triangle. The angle here, theta, is equal to pi over 4. So that's what they were saying in that solution there. The sine, let me use a different color here. The sine of the sine inverse of the square root of 2 over 2, while the sine inverse inside stuff here becomes just pi over 4. And then this just becomes the sine of pi over 4, which, hopefully you remember from a previous class. This is just the square root of 2 over 2. And that is our answer. So notice in this case, it seems like the sine and the sine inverse essentially just cancel each other out. And then the answer ended up being just what was on the inside of the parentheses. Okay, very nice. But let's take a look at the next one here, because the next one is going to be slightly different. The next problem was finding, and let's see if I can just block this off here, the sine inverse of the sine of pi. Okay, well, we need to ask ourselves what the sine of pi is. The sine of pi, again, you should remember that from pre-calculus. But, here's the graph, a rough sketch of the graph of sine. It starts at 0. At pi over 2, we have at 1. At pi, we are down back at 0. So the sine of pi is 0. So then this becomes the sine inverse of the sine of pi, which is 0. This becomes the sine inverse of 0. And so we can actually use this graph that we graphed from before. And remember that the sine inverse is actually defined from negative pi over 2 all the way up to pi over 2. So the sine inverse of 0 is just 0. We can see it from this graph right here. So the answer is 0. And you can see that, well, wait a minute. We applied the sine inverse to the sine to pi, which was being applied to pi. Why did we not get pi? Why did these not cancel and we get pi, but instead we ended up getting 0 as our answer? And the answer has to do with domains, and this is what they go on to explain in the book here, down here where I'm highlighting. The inverse function is supposed to undo the original function. So why isn't the sine inverse of the sine of pi equal to pi? And so let's just try to kind of break this down a little bit. It says, let's see here. Recalling our definition of inverse functions, a function f and its inverse f inverse satisfy the conditions here. F of f inverse of y is equal to y for all y in the domain of f inverse. So this, let me highlight it. This statement here is going to be true as long as y, this value, is in the domain of that function there. Okay. And same thing for this here, f inverse applied to f of x is equal to x for all x in the domain of f. So this, they essentially cancel each other out if x is in the domain of f. So what happened here? The issue is that the inverse sine function, sine inverse, is the inverse of the restricted sine function defined on the domain from negative pi over 2 to pi over 2. Therefore, for x in the interval from negative pi over 2 to pi over 2, it is true that the sine inverse of the sine of x is equal to x. However, for values outside of this interval, the equation does not hold, even though the sine inverse of the sine of x is defined for all real numbers x. So let's go ahead and take a look one more time. So what was the issue here? Remember that sine inverse is the inverse of the restricted sine function. This sine inverse will undo everything that the restricted sine does. The restricted sine function, which we called earlier, I believe we called it g of x equal to the restricted sine of x. This was for x values in the interval from negative pi over 2 to pi over 2. So wait a minute. This would essentially only work if x was in this interval. But notice that this value that was plugged in this case was pi, and pi is greater than pi over 2. So it's outside of this inverse. So this sine function here that we're using is not the restricted sine. And therefore, when we apply the sine inverse to it, it is not going to necessarily exactly undo what the sine did, because the sine inverse is the inverse of the restricted sine, not the original sine function that we learned about in pre-calculus. Okay, so you know, a little how do I say? Yeah, it's a little intricate there, but yeah, it's cool stuff. All right. What about sine of sine inverse of y? Does this have a similar issue? The answer is no, right? So when they're flipped around the other way, so let's go ahead and go and take a look at the sine of sine inverse of something. So it says, since the domain of sine inverse is the interval from -1 to +1, we conclude that sine of sine inverse of y is equal to y if y is between -1 and +1, and the expression is not defined for other values of y. So yeah, so if we essentially, if we have the sine on the outside, the domain of sine can be a lot larger than the range of sine inverse. So you'll always be able to take the sine at the end, and it will just give you whatever the input value was, because the sine inverse is the one that has the restricted domain. All right. So at the end of the day, if you just show your work, if you kind of write out the problems, this will all end up working itself out. This only kind of runs into issues if you're trying to take shortcuts, right? If you're one of those who says, well, yeah, I think these cancel each other out. That may not be true, as we just saw, in this case. Sometimes they do, sometimes they don't. So, it's up to you. I would just recommend just writing out your work each time, and then this issue will work itself out. All right. Okay, so here we have, now let's take a look here. It says the sine of sine inverse of y is equal to y if y is between -1 and +1. But y has to be between -1 and +1 because that is the domain of the sine inverse. If y was outside of this interval, then you could not plug it into the sine inverse of y, and therefore the expression would not be defined. Whereas the other way around, the sine inverse of x applied to the sine of x is going to be equal to x if x is in the interval from negative pi over 2 to pi over 2. But as soon as we choose an x value that is outside of the interval, like x equals pi, as we saw in the example from before, pi is outside of the interval, well, the sine of pi can still be computed because technically we can then use just the regular sine function and evaluate that, but it's no longer on the restricted domain, and therefore the sine inverse function is not going to necessarily undo what the sine function did. Similarly, for the cosine, there's similar arguments there. The cosine of cosine inverse of y is equal to y. And then we run into similar issues here with the cosine of x, or the cosine inverse of the cosine of x will be x if, essentially these do cancel if x is between 0 and pi, including 0 and pi. And then similar properties hold for the other trigonometric functions. This video is really long, so let's go ahead and just finish it up by quickly doing some of these problems here. Okay, so yeah, they do one right here. This one is kind of nice. Maybe we'll just do one because this video is very long. Now, 5 pi over 4. 5 pi over 4. Okay, so let's go ahead and take a look at this problem here, part C. And I'll write everywhere because just to see. So we're going to look at the cosine inverse of the cosine. So we could ask ourselves, are these going to cancel? And well, the domain of the restricted cosine function is from 0 to pi. Well, 5 pi over 4, pi is 4 pi over 4, and we see that 5 pi over 4 is outside of that range from 0 to pi. So these are not going to cancel, and so you actually just need to show the work. So let's find the cosine of 5 pi over 4. The cosine of 5 pi over 4, this is 0, this is pi over 2, this is pi, and this is 3 pi over 2. Now 5 pi over 4, we just said that is larger than 4 pi over 4. 4 pi over 4 is right here. That's just pi. And so 5 pi over 4 is one more than 4 pi over 4, right? One more pi over 4. So 5 pi over 4 is pi over 4 more than 4 pi over 4. And pi over 4 is 45 degrees. That is one of our special right triangles. And so this is going to have side lengths, square root of 2, square root of 2, 2. And of course, we need to apply negative signs here because we are in the third quadrant. So we have negative 2, negative square root of 2, and negative square root of 2. And so we want to know the cosine of 5 pi over 4, right? So our entire problem is the cosine inverse of the cosine of 5 pi over 4. But we're doing the inside here. We want to know the cosine of 5 pi over 4 first. We're going to work our way from the inside out. The cosine of 5 pi over 4 is going to be adjacent over hypotenuse, negative square root of 2 over 2. Now, what is the cosine inverse of pi over, what is the cosine inverse of negative square root of 2 over 2? Well, this is what we just learned in this section. How do we evaluate cosine inverse, inverse trigonometric functions? Well, remember that the range of cosine inverse is from 0 to pi. It is very important that we know the range of these inverse functions. So this is going to be an angle theta in the interval from 0 to pi. This is the range of cosine inverse with the cosine of theta being equal to the negative square root of 2 over 2. Now, in which of these two quadrants, 1 or 2, is the cosine of the angle equal to a negative? That would be in quadrant 2. Okay. Well, the cosine, the adjacent over hypotenuse, is going to be negative square root of 2 over 2. Of course, the hypotenuse is negative and never negative, so the negative is going to go with the adjacent side. And then you see, okay, well, I can use the Pythagorean theorem. I'm not going to do it, but you can use the Pythagorean theorem to find this y value here. It turns out that this y value is going to be the square root of 2. So we want to know what angle theta from 0 to 180 degrees, if you want to talk about it in degrees, has a cosine of negative square root of 2 over 2. Well, this angle here, this angle, theta, has a cosine of negative square root of 2 over 2. Well, we are going to look at this reference angle here, and let's call this reference angle alpha, because I'm going to use this reference angle alpha to help me find the angle theta. And I think hopefully we know now that this reference angle alpha is equal to 45 degrees or pi over 4 radians. That's just by looking at the triangle. This is a special right triangle. And when we're looking at special right triangles, there's only a couple answers. It's 30 degrees, 45 degrees, or 60 degrees. In this case, it's the 45, 45, 90 triangle. So the reference angle is 45 degrees. Let's do it in radians here. We'll do pi over 4 radians. So what is the angle theta? If you take a close look at just the structure of this here, pi radians is all the way, half of a circle, right? Half of a full revolution. So pi minus alpha is equal to whatever theta is. Right, so if you go pi, you take away alpha, which is pi over 4. So then with pi, I'm going to write this as 4 pi over 4. This is equal to theta. And so that means that theta is equal to 3 pi over 4. And so our answer there is 3 pi over 4, which notice is not 5 pi over 4. Right, we could not have just crossed out cosine and cosine inverse and said the answer is 5 pi over 4. Because the answer, in fact, is 3 pi over 4. All right. And of course, they do it a lot more cleanly. If you just can do a bunch of stuff in your head, they do it in the textbook here. Let's just read the solution for part C. To evaluate cosine inverse of cosine of 5 pi over 4, first use the fact that cosine of 5 pi over 4 equals negative square root of 2 over 2. Maybe you just know that. That's basically what they did here. Okay, maybe, yeah, if you know that, that's nice. Then we need to find the angle theta such that cosine of theta is equal to negative square root of 2 over 2 in the interval from 0 to pi. And that's exactly what we were looking for here. And then they just say, since 3 pi over 4 satisfies both of these conditions, we have that the answer is 3 pi over 4. Okay, well, yeah, that's very nice. Yeah, so, I showed the work there. So that's very nice. All right, this is a very long video, so we will stop it there. Yeah, feel free to work on problems. You know what, or maybe we'll do one more here just to show one more example. Let's go ahead and do it. Let's move that aside. And of course, yeah, you feel free to stop the video if you're done. So we'll do one more just to show how to do these. Yeah, maybe we'll do part B. That one's nice. The tangent inverse of -1 over the square root of 3. So remember that the tangent inverse, somewhere along when we were reading, it said that the inverse function is an angle where was that? Oh yeah, here it is. When evaluating an inverse trigonometric function, the output is an angle. So you need to keep that in mind. when you're evaluating an inverse function, inverse trigonometric function, this is an angle, and we usually call it theta. Now this angle needs to be in the range of that inverse trigonometric function. The range of tangent inverse, we can scroll up and look at it. The range of tangent inverse is from negative pi over 2 to pi over 2. So that's how I'm figuring out which quadrants to be in. So this is going to be an angle in negative pi over 2 to pi over 2. We need a specific condition on this angle, and this is going to be with the tangent of the theta being equal to negative 1 over the square root of 3. And if you remember the acronym all students take calculus, you know that we want tangent to, or first of all, let's go ahead and look at where negative pi over 2 to positive pi over 2 is. It's in these two quadrants 1 and 4. And so, okay, we've restricted to 2 quadrants, and now we have the condition that tangent needs to be negative. So in which of these 2 quadrants is tangent negative in? That is going to be in quadrant 4. So we make our triangle, our reference triangle, in quadrant 4. And so we are looking for some angle here in quadrant 4, such that the tangent of this angle is equal to, so opposite over adjacent, opposite is equal to 1 over the square root of 3. Of course, it is negative. I always put the negative in last because, you look at the quadrant, we're going downward. So the downward value, negative, the 1 should be negative. And then the square root of 3, of course, should be positive because it's rightward movement. And then, wait a minute, this is a special right triangle that we've seen before. If you use the Pythagorean theorem, or maybe you just remember, the hypotenuse has a length too. Okay, which angle is this? Well, this angle here is going to be pi over 6. Since the rotation is, so the reference angle is pi over 6, right? The angle inside of this triangle, they are always going to be like 30 degrees, 60 degrees. Oops, this one should be 60 or pi over 3. Right, they're always going to be 30, 60, or 90, or 45 degrees. Those are the reference angles. But then what is the actual angle? Starting from the x-axis and rotating up to here, since the rotation is negative, this is going to, the angle theta that we're looking for is going to be negative pi over 6. Okay, so that's just the inside part. This is negative pi over 6. So now we are looking for, this problem then becomes the tangent of negative pi over 6. But then, wait a minute, we've just graphed the angle negative pi over 6. It's graphed right there in black. So the tangent of that angle, the tangent is just going to be the opposite side over the adjacent side. And notice the answer here is negative 1 over the square root of 3, which in this case was exactly the argument there, right? So the answer is negative 1 over the square root of 3. Let's take a look at the answer. And now it says, first we use the fact that tangent inverse of negative 1 over the square root of 3 equals negative pi over 6. Okay. I mean, and that is true, but of course, this is the section where we just learned it. This is a review, but yeah, so it's basically, yeah, there you go. Well, we should know that. Okay. And then it tells you to use the fact that the tangent, I believe there's a typo here, the tangent of negative pi over 6 is equal to negative 1 over the square root of 3. The tangent of pi over 6 is not negative 1 over, yeah, so there should be a negative in there. There should be a negative. Therefore, the answer is negative 1 over the square root of 3. All right, very nice. All right, now we are done.